In this paper, we present the experimental realization of a theoretical effect that was discovered by Olivier and Phys, in which a pair of entangled optical beams undergoing independent losses can have their non-local correlations restored by entangling the losses. We begin with a pair of beams emitted in an entangled EPR state by an optical parametric oscillator above threshold. As you can see, these beams are very well correlated in photon number. Adding 50-50 beam splitters in the path of each beam introduces decoherence, as vacuum fluctuations interfere with the EPR beams and cause them to become uncorrelated. The EPR correlations can later be restored, not by removing the beam splitters which are causing the loss, but by introducing another optical parametric oscillator which provides a second, independent source of entangled beams. These EPR beams interfere with the original beams at the beam splitters and restore the photon number correlations to the original level. This restoration is a wave phenomenon that occurs even if the power levels between the two sets of twin beams are vastly different. In addition to protecting against loss, this setup could also be used as a quantum tap, whereby two of the beams output by the beam splitters could be monitored without detection by performing measurements on the other two output beams. We use a bow tie optical parametric oscillator to produce both sets of EPR beams. This is accomplished by retroreflecting our pump beam, which allows us to pump the same cavity in two different directions. Each set of EPR beams then has identical frequencies, as is required for the correlations to be restored by optical interference. But since the beams are counterpropagating in the cavity, they can be viewed as independent. The photon number correlations are displayed as amplitude difference squeezing. In the data shown here, the red trace corresponds to the shot noise level, which is the quantum noise level of typical laser light. The blue trace corresponds to the squeezing level, which falls farther below the shot noise for more strongly correlated twin beams. Placing 50-50 beam splitters into the paths of the EPR beams introduces decoherence and decreases the amount of squeezing that we observe. The original squeezing level is recovered by interfering a second pair of EPR beams with the first. As the relative phases of the beams at the two beam splitters are varied, we can obtain squeezing recovery from both amplitude difference and phase sum correlations, thereby ensuring that our twin beams are truly entangled at the beam splitter inputs. Squeezing is not always recovered with the introduction of the second set of EPR beams, however. If the relative phases at the beam splitters are not set correctly, the photon number correlations can be completely eliminated. Squeezing is, however, recovered for many different phases. In this data, the red trace once again refers to the shot noise level, while the blue trace indicates the photon number difference squeezing. As we scan the relative phases at the beam splitters, we see squeezing recovery for any equal and opposite phases. We hope that these experimental results will pave the way for further quantum control of decoherence, which has proven to be one of the primary impediments to experimental advances in quantum optics and quantum information.